Thank you so much for this invitation, give me the chance to talk my work here, and thank you for you all being here. So my talk will be for manifold with no smooth spines, and this is a joint work with Igor Vligretic, and he's also from Georgia Tech. So the setting will be starts like we have n-dimensional manifold M. So this is a piecewise linear compact manifold. It has boundary, so this is this boundary. And we have another manifold M dimensional, and this is a closed manifold. So now we know our manifold M is homotopic equivalent to our closed manifold M. So now the question is like we're asking whether there is an embedding from N to M, and that's what we call the spine. So depending which category we're talking about, we can talk about the smooth category, topological category, and the piecewise linear category. Then depending which category we're talking about, we can define smooth spine and topological spine, PL spine, and this is defined as like what kind of category we're talking about, like the smooth embedding or topological embedding or piecewise linear embedding in from N to M. So this is our definition for spine. So this is a very classical question, and it has a long history of research, and we have a lot of results relating to this question. For example, if the dimension n is greater than m and the codimension is greater than 2, then we know like any homotopy equivalence can be perturbed to be a PL embedding. So that means like we can always find a PL spine in such setting. And there's another result like saying when the codimension is exactly 2, then we're asking what will happen. So when the codimension is exactly 2, we have the similar result as factor 1, and we need the assumption like MM is simply connected. And we have additional assumption like M is greater or equals to 5 for all odd integers, or M is greater or equals to 7 for all even integers. Then any homotopy equivalence can be perturbed into a PL spine, PL's embedding. I would mention like the first fact comes from a lot of persons' work, a lot of big mathematicians' work. It dates back to Browder's work, Casson, Hefflecher, Sullivan, and Wolf. And for the second result, it dates back to the classical result of Capel and Shannon using the higher dimensional surgery. So now you're asking, what about dimension 3? Because we kind of know some result for dimension 5 or dimension greater or equals to 6. So what about dimension 4? This is also one of the one type of manifold people are very interested in. So if we are studying dimension 4, then Matsumoto in 1976 give the first example, which is piecewise linear but spineless four manifold. And the four manifold is homotopy equivalent to the torus T2. And he constructs such example that it does not have any PL spines. And this is also using the higher dimensional surgery theory. So this is some history, but recently we also have some new results for this kind of question. So recently, we can use some modern tools from Higgs flow homology. This is the work of Littman and Levine. So they use Higgs flow homology to find some four manifolds, which is spineless and is also homotopic equivalent to S2. So this is simply connected and solves a problems in the problem list, in the Kirby problem list. But also it worth to mention like the work of Lisa Piccarilla and Kyle Haddon. that they use the knot trace and the trace embedding lemma to find to study questions about spines. Lisa, Karila, and Hayden. Sorry. And also, I want to mention the joint work of Feller, Miller, Nagel, Austin, Powell, and Ray. They kind of also use the modern theory of shake genus to study the questions of spines. So now I'm going to move to our setting. So in this talk, we'll assume like our full manifold M. So this is a full manifold M. It always has a PO spine. But then our question is whether this manifold M has smooth spines. And we're going to construct examples about for manifold that has PL spine but no smooth spines. And trust me, in the rest of the talk, you'll see like knot theory, link theory, Higgs flow homology, hyperbolic geometry, etc. So I believe like every piece you could see something that you're interested in. So I'm pretty excited for that. But before I talk about the main theorem, I want to say like our abstraction comes from two places. The abstraction for the existence of smooth spine comes from two theories. One is from this classical higher dimensional surgery theory, given by Capel and Shannon. And the other tool we're going to use to give this abstraction is from the modern tool, which is given by Osho and Szabo, and it's about Hegel flow homology. Okay, so I will just like use all, now the rest of the talk, my notation is always like M denotes this full manifold and S is this PO spines. So there are two cases. If S is locally flat, then actually this is a very good case for us because every locally flat spine, we can perturb it to be a smooth spine. So it is always smoothable by a result of Rook and Sanderson, which is 68. But now we can go back to the case like, oh, there are some non-locally flat points in our PL spine, but then we can use a PL piecewise linear homeomorphism to assume there's at most one non-locally flat point. For example, this is our surface. It maybe could be a PL spine, but now assume like there exists one non-locally flat points like here. Then what we're interested in this work is like we're interested in the neighborhood of the singular point, and the neighborhood is just a small ball B4 for this singular point. And then we see the intersection of this boundary, which is S3, and our PL spine, which is a two-dimensional surface. So you can see like this is the intersection, though I draw dots in this picture, but by dimension counting, you know, like this is really one dimension. And we actually know it is a knot, which we called it as a singularity knot. So both our result and our abstractions comes from the property of the singularity knot, and it was very surprising, like the local property of the singularity knot actually give a global restrictions about when this manifold admits a smooth spines. So the first main result is saying if the singularity knot K has non-zero off invariant, then M has no smooth spine. This is the first abstraction. The first abstraction, this off invariant is a not invariant. If you're curious about what it is, you should think like when we have a knot in S3. So this is S3. When you have a knot in S3, you can see the cipher surface in S3, and then there is some like matrix, intersection matrix for this cipher surface, and you can just compute the off invariant from the matrix corresponding to the cipher surface. So this is one abstraction. The second type of abstraction we're using the Higgs flow homology. So we're saying like if the singularity knot K is an L space knot or connect sum of L space knots or is alternating knot with signature smaller than -4, then our full manifold M has no smooth spines. Great. So this is our second abstraction. So for people working Higgs flow homology, it might be just easier for you to understand the L space knot or connect sum of L space knot. But I just give some simple words to explain what this means. We have seen Higgs flow homology in this morning from Christine's talk. But in a simple word, Higgs flow homology is a package of 3 manifold invariants. If I talk about the rational homology sphere, sorry, I use M again. Let me use another notation. Let me maybe use W as the 3 manifold, which is a rational homology sphere. So we say this is an L space if it has the simplest Higgs flow homology. So in this sense, like in the sense of Higgs flow homology, this could be the simplest 3 manifold you can think of. So then what is about the L space knot? You have a knot K inside S3. So if there exists a surgery such that the surgery along this K is an L space, then we say the knot is an L space knot. I think the most interesting fact to know about this L space knot is like all edge break knot are L space knot. And if you don't care about edge break knot so much, then I think you might care about the torus knot. So all torus knots, they're special families of edge break knots. So they're surely also L space knot. So this is 2 main abstractions here. But before I give the main proof of our theory, I think like it would be more interesting to give examples. So the way we construct spines or full manifold is actually very standard. So just give any knot K inside S3. So this is B4 and the boundary is S3. We have this knot K here. We actually can attach a 2 handle. The 2 handle always denoted by D2 cross D2. So what we see, so the K is here, the knot is here. We don't know whether it will bounce a smooth disk or topological flat disk or locally flat disk inside our B4, but we always know it will bounce a cone disk inside our B4. And then in our 2 handles, this co-core of these 2 handle will bounce another smooth disk for this knot K and to close it up. So at the end, we'll just get S2 with 1 cone point. And this full manifold is just the union of B4, union with 1, 2 handle. It has a PO spine, which is this S2, and you have this cone point inside it. The cone point, if you take the neighborhood and you see the singularity knot, it exactly contains the information of the knot we start with, which is K. So that's one example to construct the full manifold, which has a PO spine with our knot K. And we can check whether the knot K satisfies the property of our abstraction. Then we'll conclude like whether there is a smooth spine or not. And moreover, you can just replace this 2 handle by a higher genus handle. For example, I can just replace this D2 cross D2 by sigma G cross D2. I mean, this sigma G is a genus G surface, but I need to throw away a disk so that it has a boundary. It has a boundary S1, and then you glue the boundary, which is the torus along this knot K, as what we did for the standard 2 handle. So in this case, what you get is also a full manifold, but now this PO spine is just the genus G surface, and this is still the cone disk, and this genus G surface comes from the handle you're attaching this to your full ball. So this is the topological construction for the four manifold, which has the PL spine, but we will check whether it has a smooth spine or not by using our abstraction. So by a result of Haddon and Livingston, we know like there exists a family, infinite many family of this family has infinite many knots, a family of topological slice, not K. So we already know like this family has this topological slice. So we know like this knot K will bound a topological disk inside our B4. But then we need to check like whether this K will satisfy will pass to our abstractions or not. And we find like in this example, they have the chain complex in Hegel flow homology, which is the same, which is homotopy equivalent to the torus knot. So it does not pass to our abstraction, so that we know it does not have a smooth spine. So this is the first family of examples we have. And another type of example is from hyperbolic geometry. So another type of example from hyperbolic geometry.
Wait, Bebe. So is
Yeah.
there, did you forget to write the second half of this red statement, Haddon and Livingston? What's the second half?
Oh, I did, yeah.
Because there's a sampling, yeah, sure.
Yeah, so what I'm trying to say, like we have a corollary from their example is for any genus G and any Euler number E, there exists a smooth oriented four manifold such that it has no with no smooth spine. And they have topological spine, locally flat spine. And the spine has genus G, which is genus G and Euler number E. Does this make sense? So yeah, great. So this topological locally spine comes from the fact that our knot is topological slice. But then we check the chain complex in flow homology, and we find like it is the homotopy equivalent to the torus knot. So our abstraction can help us find like there's no smooth spine. So this is one family of examples we did. Thank you, CD, for pointing it out. Another thing I want to say is this hyperbolic four manifold. So we use the Bohr model for hyperbolic manifold. So now this is B4. This is a Bohr model for hyperbolic manifold. And if we just consider a totally geodesic disk inside the B4, and we use an angon, here I can just draw an angon. And we just tie it on this disk, like this way, etc. You can tile your angon for the whole disk, which is totally geodesic, and we can just find some discrete isometry subgroup preserving this totally geodesic disk, such that we can just do the quotient of your disk with your group, and this is homotopy equivalent to H4 over gamma, and you find like this is exactly the trivial vector bundle over a genus G surface. So this is not so interesting because it's a trivial bundle and not so many topology information will contain on that. But then Gromov, Thurston, and Lawson, they did something very interesting for this example. Let me find where I am. Yeah, so this is a result of Gromov, Lawson, and the Thurston. What they did is like, now you don't tile the totally geodesic D2, but now, like, for example, I have one piece of this 8 ohms and the other one I will attach here, but now I won't attach in the same plane. I will just do some angle. Does that make sense? And also for this for this neighborhood, I will just tile another 8 gon. But now I also don't need to do the same plane. I can just give another angle. So at the end, like you're tiling the whole D2, but now it is not a totally geodesic D2. It just have like here, sorry. It just have like this one and then do another one and do another one and do another one, do some rotation. So this is like, okay. Yeah, so now you're just still get a D2, but now this D2 is not totally geodesic. So you still get a vector bundles over your genus G surface, but it's not trivial. And it has some Euler number. So by their construction, you see like the singularity point comes from here. Because like you're now not tiling them in a totally geodesic plane, you're tiling them with some angles. And this gives you some knot. And what they use is the torus knot or and if you pass to some finite cover, that is just the connect sum of the torus knot. So we can still use our abstractions to say, oh, in their example, it does not contain a smooth spine. So that's another example. And I want to mention, like, if you care more about geometry, we can do more. So this is just the hyperbolic geometry. So it has the sectional curvature, which is -1. It has the constant sectional curvature, but actually we can do any negative curvature. So go back to this example. We know like for any knot K, we can either build a four manifold with the PL spine S2, or we can build a spine with genus G surface and with any Euler number. This is exactly a topological construction. So how the geometry will put in. So I'll just give this as an example. So this is a four manifold. And it is just the union of B4 with two handle. It doesn't have nothing to do with the geometry now, and we don't know the curvature. We don't know it's negative or positive. But now we do the triangulation of these four manifolds. And for each piece, we still don't know whether it's flat or whether it's negative, but then we'll replace each piece by some hyperbolic manifold with boundary. And then we just glue this hyperbolic manifold with boundary together along with the pattern of our original manifold under the triangulation. And this will give us some piecewise hyperbolic manifold. And you can do some Riemann-ization process to make it like the curvature is negatively pinched. And this is called the alternatus Riemannian hyperbolization process. So at the point I want to say like another example we can do is like for any knot K and any genus G and Euler number greater than 0, you can just construct some four manifold with negative pinched curvature. Such that it has a PL spine, which is the genus G surface with Euler number E, but no smooth spines. And this is using the alternatus hyperbolization process. Okay, great. So I say something about Hegel flow homology, I say something about hyperbolic geometry and negative pinched curvature, and also some link theory. Hope that will be interesting for you. So at the end, in the last 5 minutes, I'll just give some sketch of the proof, because the proof, you see like it comes from 2 different theory, and actually the flavor will be very different. But I think like it's good just to know what is the main philosophy in either of the proof. So if you remember, theorem 1 is about the off invariant. The abstraction comes from the off invariant of our knot K. And how does this comes into the picture? So recall like our manifold is M, this is a four manifold, and we have our spine is S, this is a PL spine in M. So in order to use the higher dimensional surgery theory, we cannot do in dimension 4. So what we should do is we need to leave the dimension to dimension 5. And how can we do that? We just do the product with S1. So M will become M prime, which is M cross S1. and S prime will be S cross S1. So now this is 5 dimension, this is 3 dimension. We know like there is a homotopy equivalence from M prime to S prime, so there's a map from our 5 manifold to the 3 manifold. And assume like there is another locally flat spine, L inside W by assumption, then I get another L prime inside M prime. So I just restrict our map to L prime. So I get a map from L prime to S prime. So this is our map. So now the map actually is homotopic to a diffeomorphism because this is locally flat. So we have 2 things. One thing is this normal invariant of G. And the other thing is this normal invariant of S prime inside W prime, M prime, sorry. So this is by the higher dimensional surgery. The left-hand side must equals to the right-hand side. But we find like the left-hand side always equals to 0 because this is a locally flat spine. And this map G is homotopic to a diffeomorphism. So that's why the left-hand side is always 0. And we did some work to find the right-hand side, the normal invariant of S prime is equals to the off invariant of the knot K. That's why we find one obstruction should from the off invariant of the knot K, and that's why it comes into this picture. And that's the idea for the first result. And the second theorem, if you remember, the obstruction comes from L space knot or connection or signature, but they have the same kind of flavor, and we use the same tool to prove. So I want to just give you a heads up like why it is like that. So remember, M is this 4 manifold, and let's say S1 is this PO spine, and S2 is this smooth spine or locally flat spine. So what we did is like we first of all consider the complement of the neighborhood of S1. So you can see now this is a 4 manifold with boundary, and then I union another 4 manifold with boundary, which is the complement of M inside S2. And I attach these 2 manifolds together along the boundary of M. So that now you see this is a 4 manifold for sure, but now you see like it has 2 boundary components. One boundary component comes from the neighborhood of S1, and the other boundary component comes from the boundary of the neighborhood of S2. And in the middle is this 4 manifold. Moreover, you can observe like because they're spines, so this is a homology cobordism. And then you're wondering like how the Hegel flow homology will enter this picture, because so far I'm just talking about topology. The role of Hegel flow homology is because like this is a 3 manifold. This is also a 3 manifold, but this 3 manifold has a very nice description. It's a surgery along our knot K connection with the bromine knot inside the connection of S2 cross S1. So there are 2 G copies. And this is there's another description for this boundary. And you just need to replace this K by R naught. And you do the same thing. So you have this description for this 3 manifold. And this is where the Hegel flow homology comes into the picture, because like you can compare the Hegel flow homology invariant for this 3 manifold, and it must be equals to this 3 manifold because it's a homology cobordism. And the same we're using is the D invariant. So that's the sketch of the second proof. I hope like I can at least makes you have feeling how the theories get into the picture. But I think it's 45, and I have said all the things I want to share. Thank you so much for your attention, and thank you for like distraction for the cats.
Let's thank Bebe for a really interesting talk. Do we have any questions for Bebe?